Okay, so let's get started. Here's Taylor's theorem that we wrote last time. Let me remind you, we're looking at a function. It has to be differentiable n plus 1 times, because we're considering the derivatives, in a neighborhood of the point A. The A is the point with respect to which we're doing the Taylor expansion. That's what it's called. And most of the examples that we did, A was just 0. If you take any point x in that neighborhood, then you can write the function as the Taylor polynomial. This was the Taylor polynomial, which we wrote the formula for. Remember, the coefficients were the nth coefficient had the, or the kth coefficient had the kth derivative of f calculated at a divided by k factorial, plus a remainder, and the remainder is given by this formula, which we said this is called Lagrange's form, Lagrange form of the remainder. There are other ways to write it. Lagrange form of the remainder. Namely, there is some point C, which we don't know what it is, between a and x, such that the remainder at x is given by this, this expression, which resembles what you would like to be the n plus first coefficient in the expansion, but it's not at a, rather it's c. Okay? And we saw that this reduces to Lagrange's theorem when n equals 0. And one more thing that we said is that just like for the linear approximation, Taylor polynomial of degree 1, the tangent line, the remainder satisfies that it goes to 0 as you approach the point, even when you divide by x minus a to the n. So, so this we also mentioned, and so this is always true. So as you get closer and closer to the point A, your approximation becomes better and better. Okay? Tends to 0. The error tends to 0. Okay. What I want to do now, in order to help us absorb and relate to this theorem, is to do an example. Okay? And the example is going to be the following. So let me remind you, recall, remember how we defined E? The limit of what?
1 plus 1 over n.
Right. We defined E to be the limit of 1 plus 1 over n to the power n as n goes to infinity. We said, okay, this is a sequence. We didn't do the full details, but we mentioned that in fact this sequence is monotone, increasing, and bounded between 2 and 3. We mentioned that. Okay? And by a theorem that we had for sequences, since it's monotone and bounded, it converges. And we said, okay, let's give the limit a name. We call it E. That's how we defined E. So at this point in time, all we know about E is that it's some number between 2 and 3. Right? Maybe you know that it's something like 2.71 ... but why? Why is that true? How do you find that? Okay? So what I want to do now is I want to calculate E. I want to know what E is precisely. I want to somehow find those 0.71, etc. Okay? And the way we're going to do it, is to use Taylor's theorem. Okay? So this is one recall. This is a fact from quite a while ago when we talked about sequences. But there's another fact from last time. We showed that for e to the x, the function e to the x, can be written as its Taylor polynomial, which we calculated explicitly. It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial. So this was Pn of x. This was the Taylor polynomial of the function e to the x, or the Maclaurin polynomial, around a equals 0 of degree n. But this is by no means equal to the polynomial. How can I correct this? Right. There's an error term. So plus r n x. Good? So, if I want to calculate e, I can, for example, plug into this function x equals 1. So e itself, which is e to the power 1, is equal to, I'm going to plug in 1 here, so I'm going to get 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus plus 1 over n factorial. And again, that's not going to be an equality. There's going to be a remainder. There's going to be an error. So I'm going to replace this equal sign with a squiggly equal sign. And what I mean when I write this is that this is not an equality, but it's almost an equality. It's close. Okay? And what I want to know is, how close is it? Okay? So, what I'm going to do is, I'm going to require some limitation on the error I'm willing to accept. Okay? And that limitation is going to tell me how far I need to go in terms of n in order to guarantee that when I write this equality, the error is at most that limitation that I prescribed. Okay, so let's write that. Suppose we require the error to be at most 1 over 100. So we're willing to have an error of at most 1 over 100. Okay? And you can similarly run the entire thing with 1 over 1,000 or 1 over 10,000 or 1 over 1,000,000. Okay? It's the same idea. So suppose this is what we want. Let's write what is the remainder in this case. Okay? So the remainder, r n of x, in absolute value, we want this to be less than 100. I'm writing it in absolute value because I didn't say if I care if the error is, if what I get is too big by 100th or too small by 100th. So in absolute value, we want this to be less than 100th. Let's write what this is. So remember the formula, the Lagrange form of the remainder. Let's look at it again. Here it is. And now I have to put in all the concrete details from this example. So the function is e to the x, right? So its n plus first derivative is still e to the x. Do you agree? Evaluated at the point c, it's e to the c. Do you agree? And everything else is going to be the same. So Rnx is e to the power c, that's the n plus first derivative evaluated at the point c, divided by n plus 1 factorial, times, so let me write here. What is our a? What is a? When we wrote this expansion of e, a was 0, right? That's the point around which we're doing the Taylor polynomial. What is x in this example? x is 1, right? That's the point where we're evaluating it. We're doing e to the power 1. We're putting x equals 1. What do I know about c by the theorem? C is between a and x, right? So c is between 1 and 0. Do you agree? Okay. So e to the c n plus 1 factorial, and then I have x minus a to the power n plus 1. But x minus a is just 1. To any power, it's just 1. So this is actually the remainder. Do you agree? Did everybody follow? Questions? Yes?
C. Why is it less than 1?
That's the theorem. When you find the Taylor polynomial around a, and you take any x in that neighborhood, look at the theorem on that board, okay? Take any x in that neighborhood, there's going to be a c between x and a. Let's look at it together. A neighborhood of a, take x to be any point in that neighborhood, there's going to be a c between a and x, such that the remainder is given in this form. Okay? Okay, so back to our calculation. So e to the something is always positive, as is a factorial, so we don't need the absolute value here. This is always positive. And remember what we want. We want this to be less than 1 over 100. That's what we're seeking, right? That's what we want. What can I say about e to the power c? Greater than 0 is true, but that's not the direction that I want. I want to write less than something. Can you give me an upper bound for this? E. It's since c is less than 1, e to the power c is clearly less than e to the power 1. So this is still true. And what do I know about e from our previous knowledge? Between 2 and 3, so it's clearly less than 3. These are kind of rough estimates, but that's all I can write at this point, right? I don't know any more about e. Does everybody agree to this? And what we want now, what we want is this to be less than 1 over 100. Want. Is it always going to be less than 1 over 100? Clearly not. It depends on what n is. If n is big enough, it is. Do you see that? Do you agree? So since we don't want to work too hard, we can take n right away to be 1500. Then clearly this will hold, but then our Taylor polynomial is going to be of degree 1500. We don't want to do that. We want to find the smallest n for which this will hold, right? And how do we do that? We just start plugging in n's, okay? So let's see. For n equals 0, we get 3 divided by 0 plus 1 is just 1, factorial is just 1, is 3 less than 1 over 100? It's not. So we can't stop at n equals 0. What about n equals 1? We get 3 divided by 1 plus 1 factorial. That's 3 over 2. Is 3 over 2 less than 1 over 100? Not quite. So we have to move on. For n equals 2, what do we get? We get 3 divided by 2 plus 1, which is 3, factorial. So we get 3 over 6, which is 1/2. Is 1/2 less than 1 over 100? Not yet. We move on. N equals 3. We get 3 over 4 factorial. That's 3 over 24. We get 1 over 8. Is that less than 1 over 100? Still not. Moving on. N equals 4. We have to multiply this by 5. We get 1 over 40. Is that less than 1 over 100? Not yet, but here it comes. You can feel it coming. N equals 5. Yes. So what do we have to multiply this by? 6, so we get 1 over 240, finally. Is that less than 1 over 100? Bingo. So, what do you mean the only way to do it? You can.
Like, what if it was 1 over 1,000? You'd be like plugging it, or 1 over 1 million. Like, you're just supposed to plug in numbers until it.
Yup. So if you were looking for 1 over 1 millionth, the error to be very small, you'd have to move in further down the ends, and well, further up the ends. But probably you would see right away that you can jump a few. You're not going to get there so fast, so you would, eventually find it. Yeah. Okay. So do you agree that for n equals 5, the error for n equals 5, R5 of x, by this calculation, is indeed less than 100th? Do you agree? What does that mean? It means, back to this board, it means that if we stop here at n equals 5, if we take the Taylor polynomial P5, the Taylor polynomial of degree 5, then we're guaranteed that whatever we find here is not going to be equal to e to the power 1, but the error, it's going to miss e to the power 1 by at most 1 over 100. In fact, by at most 1 over 240, which is even better. Right? So we need to calculate this and up to n equals 5. So the conclusion from this calculation, what we can deduce is, take P5. So we get that e to the power 1, which is e, equals 1 plus 1 plus 1 over 2 plus 1 over 3 factorial, which is 6, plus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120. Stop here. Replace the equal with squiggly equal. So E is about that. What do I mean by about that? I mean the error is less than 1 over 100, but we found that in fact it's less than 1 over 240. Clear? Now do we know what E is? Well, yeah, we can actually add these things up. How do we do that? No calculator. No calculator. Now I'm saying no I'm saying no calculator not because our ancient ancestors did it without a calculator. They did. That's exactly how they did such things. But in fact, how does the calculator do it? How does the calculator know what is E with 1,500 digits after the decimal point? It runs algorithms, maybe not precisely this one, but things like this. That's how it knows. There's no magic going on there. Okay? It just saves you doing this, but that's what the calculator does. Okay? Let's do it. Let's be calculators. So how do we actually find this? Right, we have to do a common denominator of 120. So what do we have here? We have 120 plus 120 plus 60 plus 20 plus 5 plus 1. And now we can add these up. So we have 240, 326 over 120. That's even clearer. And if we want it in decimal form, what do? Don't say plug it into the calculator. We divide. Do you know how to do long division? Let's do it. 326 divided by, we're going to need more space, I'm guessing. There are several conventions of how to write this, so I hope you're able to live with this convention. Some people do it. I'm doing it the way I'm used to. You guys are going to have to adapt. So 326 divided by 120, it's 2. 2 times 120. The logic of writing it in this direction?
So you're writing the 2 up there?
Yeah, 2 times 120, 240. Now I subtract. So what do I get? 86. 86 is not, well, I have to pull down an extra 0. And here's the decimal point. That's why I wrote it up here. 860 divided by 120. Well, I know the answer. It's going to be 7, of course. 7 times 120 is 840, right? 7, yeah. Subtract, you get 20. Pull down another 0. 200 divided by 120 is 1. Multiply, you get 120. Subtract, you get 80. Pull down a 0. 800 divided by 120, it's not going to be 7, so it's going to be 6. 6 times, that's 720. Subtract, you get 80. That's it. From here, it's going to repeat itself. Do you agree? So it's going to be 6666, ... That's it. So this equals 2.7166 bar. And that's E. That's E with an error of, at most, 1 over 240. Okay.
If you went to P5, you also get a period or not?
Excuse me?
If you went to P6.
If I went one more, if I took n to be, let's do that in a second, just to see. But by the way, if you plug it into the calculator and get, I wrote it somewhere here. Yeah, so calculator will tell you, not the approximation, just plug in E. It will tell you that E is 2.718281 ... So you can see that our error is indeed of the magnitude of 2 over 1,000. Yeah, we found it with an error, but that we didn't care about. It's in the range, and you can see the magnitude of the error is about 2 over 1,000, which is 1 over 500, so it's smaller than this. Okay. Now suppose you wanted the error to be at most 1 over 1,000, for example, and not 1 over 100. You would go back here to this board. You would write want and add a 0 here, 1 over 1,000. You would see that n equals 5 is not sufficient. You would take maybe n equals 6. N equals 6 will already be enough. So you would multiply this by 6, right, from here to, no, by 7, and plus 1, and you would get that it's enough. Okay, and then you would take, do you agree? Does everybody see that? And then you would take here one more term, so the next one would be 1 over 720. Add it, do a common denominator, you'd get something that's even closer, and your calculation would be even closer, and your error would be at most 1 over 1,000. Clear? Good? So this is not just for the sake of history. This is the way we actually, as in we with the batteries, actually do things today. Okay, there are various algorithms. Some are faster or more efficient in many senses, but that's what's going on inside that little calculator of yours. Okay, it doesn't have like a table and it looks up all the values. It does some algorithm. Yes.
So then, to be precise, what does the calculator say, like, to be the most error?
Well, the calculator can only present, depending on how new it is, a certain fixed number of digits after the decimal point, right? So suppose it can present, the old calculators would present only 8 digits, right? So it would only go, you would know that your 8 digits are accurate. The error is somewhere in the 9th digit and further, but you can't even see that on the calculator. If your calculator can present 250 digits, then just the same. Clear? So this is an application of Taylor's theorem. That's the idea of doing approximations. And this idea is all over mathematics and applications of mathematics. And this is our first flavor of it. Okay? You want to calculate E, and you can run this for various things. You can calculate, for example, sine of 1. That's what we started with. Remember, we said, how do we know what is sine of 1? Run the same idea. Okay? Do a similar thing. And moreover, and we'll see a few examples, and you'll see a few more in your homework and in discussion, you can do other things other than just calculate values using this, and we'll do it in a second. Question? Yes?
So we use the function of e to the power of x, right? And said x equals 1?
Right. We took the Taylor polynomial corresponding to e to the power x, and we wanted to evaluate it at x equals 1, so that's how we got this.
So what if we want to use e as 1 plus 1 over n to the power of n?
So I don't understand the question. That's how we defined E, as the limit of this sequence. But this doesn't tell us what E exactly is, right? All we knew about it from the construction is that it's less than... You can explore it more inside that, the proof of that, of the fact that this sequence converges. We didn't do the details. But in showing that it's in fact less than 3, you can actually find a more tight upper bound. But you can do it in other ways, okay? So before I give you one more example of a totally different application of Taylor's theorem, I want to point out something. In this example, it is true that the bigger the n, the greater the accuracy. Okay? In this example, we had an example last time where no matter how big an n you took, you didn't do any better. Remember that example? E to the minus 1 over x squared or something. The polynomials didn't change when n grew. Remember that? Yeah. So one other thing we're gonna want to know, and that's not included in the Taylor theorem the way we stated it. One other thing we're going to want to know is, when are we guaranteed that by working harder in terms of raising the ends, are we doing better? Are we lowering the error? Okay? Question? Yes?
Is my assumption correct that the limit as n approaches infinity of 1 plus 1 over n to the n is actually, if you multiply the bracket out, that you will get the Taylor series?
Okay, I'm not sure I'm following your question. Maybe we can discuss it over the break. Okay? Okay, so what I want to do now is another example of an application of Taylor's theorem. Where did I put that? There it is. So here's a totally different application of the theorem. And then we'll mention the conditions which guarantee that bigger ends do better. Okay, so here's another example. Suppose we want to calculate the limit as x goes to 0 of sine x minus x divided by x to the power 3. This is just a limit calculation, good old limit calculation. And you can easily observe that this is a situation of 0 over 0, right? You can L'Hopital this easily and solve it. Okay? But I want to do it differently, not via L'Hopital. And what I'm going to do is I want to replace the thing that's tricky here is this sine function. The rest is kind of just powers of x. I want to replace this sine of x with its Taylor polynomial. Okay? So I'm going to write the limit as x goes to 0. And instead of sine of x, I'm going to write x minus x to the power 3 over 6. Remember, this was sine of x. This was the Taylor polynomial of degree 3. Remember this from last time? Is this equal to sine of x? No. What do I have to add? Right. So I'll write plus r3 of x So all of this is sine of x. Then I'm going to write minus x. This minus x is this minus x. And divide this by x to the power 3. Do you agree that this is precisely the same thing?
Didn't you say R4?
Because I took the Taylor polynomial of degree 3, P3 corresponds to R3. R3 is going to have 3 plus 1 factorial in the denominator. Okay? Good? Okay. The x's here cancel. And this x to the power 3 over 6 over x to the power 3 gives me, so let me write that, limit x goes to 0. I get negative 1 over 6 plus, and now I have here this R3 of x divided by x. Sorry, by x to the power 3. Do you agree that this is what I'm left with? Good?
Can you say about the
I canceled x and minus x. They're gone. And I divided here. I wrote it as this over this, and the x to the power 3 canceled. That's all that survived. And this I just left untouched. Okay, good. Now, the property of the remainder is that it goes to 0 as x goes to 0. But it's a stronger property. It doesn't just go to 0. Look at this board again. We wrote it down here. The remainder goes to 0 when x goes to a. A is 0 in that example. Even when you divide by x minus a to the power n. Okay? So this is something we mentioned last time. So this is the more powerful statement about the remainder becoming smaller as you approach the point. So do you agree that when a equals 0, we just get Rnx divided by x to the n? So in this case, in our example, I can say that R3x divided by x to the power 3 goes to 0 as x goes to 0. So what is this limit? It's just negative 1 over 6.
Why is Rn of x going faster to 0 than x?
So that fact that we just wrote down there is something we mentioned last time. We didn't prove it. The proof seems innocent at first glance if you think of the Lagrange form of the remainder, but it's not. Okay? And I don't want to get into the details. There are delicate issues there. Okay? In order to really prove that formally, you have to work a bit. Okay? For any n, as long as you take the same n here and here. Okay? So here it's R3 divided by x to the power 3. And you can, by the way, verify this. So verify using L'Hôpital. It's easy.
We're getting here that
We calculated the limit.
the most that we approach to 0, the error is going to be less and less each time.
Well, that is a weaker statement. The fact that the error becomes smaller as you get closer and closer to the point is weaker. We're saying, moreover, even when you divide by x or by x squared or by x cubed, it will still go to 0 as x approaches 0. That's making it more challenging for it, right? Because now it's a 0 over 0 situation. Still it will go to 0. Okay, one way of thinking of it, okay, and this is what I said, that it's the naive way of thinking and it's not accurate, but think that the remainder, okay, I don't want to say Taylor series yet because we're not there yet, but think that the remainder kind of hides inside it higher degrees of x's, right? The remainder is what you would get if you would continue the polynomial to higher and higher degrees, right?
How do I know that it's small degree than x to the power of 3?
That's what I wrote there as a fact, okay? That down there, that's the fact, okay? We didn't prove it. But if you think that this kind of hides inside powers of x that are greater than 3, then when you divide by x to the power 3, there are still going to be x's, and when x goes to 0, it goes to 0. That's kind of maybe a way to convince yourselves. Yes?
How can we use L'Hôpital to verify that if we don't know the derivative of x?
No, use L'Hôpital right here,
Oh.
at this step. It's easy. It's something you could have done before you even knew Taylor. Just calculate this using L'Hopital, and magic, you'll get negative 1 over 6. It's one step. Yes?
The degree of r dx has to match the power of x in the limit or not?
Yes, that's the statement. Same n. Okay, there's an n. Rn of x divided by x minus a to the n. Okay? Well, one second. One more statement. How did I know to stop at R3? What would have happened if I would just said sine x is x minus R1?
You wouldn't have that.
Right. I would have R1 here. The x's would still cancel. I would have R1 over x to the power 3. And I'd be stuck. I wouldn't know how to say anything further. What if I went beyond? What if I took the polynomial of degree 5 and wrote R5 of x here? That would be fine. The term with the x to the 5 would go to 0 because I'm dividing it by x to the power 3. It would have an x squared left in it, would go to 0. And R5 of x divided by x to the 3 is still goes to 0. Okay, so if you take a smaller power of x, it's definitely going to go to 0. Okay, so this is just an example of an application, of another application of Taylor in a totally different context. Okay? Okay. The last thing I want to do concerning Taylor's theorem, and this is actually the last thing I want to do in this chapter of differential calculus, and after the break we're actually going to start talking about integrals, is I want to give you a theorem which guarantees that the bigger the n, the more accurate the result, the smaller the error. So this is a theorem. We're not going to prove it. The proof is not hard, but we're not proving everything in this course. So let f of x be differentiable infinitely many times. I need it to be differentiable infinitely many times because I'm going to talk about Rn as n goes to infinity. Okay? Infinitely many times in a neighborhood of E. Assume, this is the sufficient condition. It's not an if and only if statement, but it's a sufficient condition. Assume that there exists a k, a constant, a number, such that if you take the nth derivative of f, evaluated at the point x, this is going to be in absolute value less than or equal to k, bless you, for all n and for all x in the neighborhood that we're talking about, in this neighborhood of A. Okay? So there is a k that simultaneously is a bound for all the derivatives on the entire neighborhood. Okay? This is a powerful requirement. It doesn't happen for free always. Okay? But if this happens, if you can show that this happens, then the remainder, Rn of x, goes to 0, not as x approaches a, that was a statement we had before, as n goes to infinity. Namely, if you make n bigger and bigger, the remainder is going to become smaller and smaller. Okay? So if the phenomena that we saw with calculating e is guaranteed to happen. Go further down your polynomial, further up the ends, up the degrees, the error is going to become smaller. How small? As small as you want it to be. Okay? So when does this hold? Is the statement of the theorem clear?
You don't need to say that small n is part of the natural numbers, or it's
Whenever we write n in this course, whenever we write n, well, not whenever. Here it's just neighborhood in. But whenever we write n as an argument, we always implicitly mean a natural number. Always. So when you see limit n goes to infinity, it's always a sequence. Okay? Always. Okay, so example. F of x equals sine of x. What are all the derivatives of sine of any order? They're all plus minus sines and cosines. Remember, we did that last time. Do you agree? So they're all bounded by 1. All the derivatives of any order, all satisfy this with k equals 1. Because they're all sines and cosines, and no matter what x is. Do you agree? Does everybody agree? So this function satisfies this condition on any neighborhood of 0. So we know that for sine, the remainder is going to go to 0 as you take the polynomial to be of higher and higher degree. Okay? So this satisfies, let's call this condition star, satisfies star, and on any neighborhood, in fact, on all of R. Do you agree? Everybody? Questions?
It means that I can put any k, or...
No, with k equal 1.
Oh.
With k equals 1. Or any k that's bigger would also work, of course, but because it's all sines and cosines. With plus or minus, they're all less than or equal to 1.
In this case, it was pretty simple to define that that 1 is an upper bound for all the derivatives.
Right.
The derivatives change, and they are not like there's no upper.
Right. This is an easy example, right?
How can you find it?
So, okay, so let's do more examples. So this is example 1. Example 2, take the function we were just discussing, e to the x. All the derivatives are all e to the x, right? Are they bounded? Is e to the x a bounded function? No, right? E to the x looks like this. It's not bounded. So how come we were able to still say this for it?
Because it's a neighborhood.
Right. On a neighborhood, if you take a neighborhood of 0, any neighborhood, let's call the neighborhood, let's make it a symmetric neighborhood. Let's call the neighborhood minus b, b. Okay? A symmetric neighborhood. Then e to the b, the value at the this is the trickiest thing in being a teacher, is remembering to say right when you mean left so you can see it the other way, right? Right? Left? Oh boy. So the e to the b is the value at the, oh boy, right side, and it's a bound for e to the x on the entire interval minus bb. Do you agree? So e to the x, kth derivative, is less than or equal to e to the power b on a neighborhood minus b, b. So this is our k. So on any neighborhood you take, the derivatives are bounded together by a specific value, and therefore e to the x still satisfies this. It doesn't satisfy it on all of R, this condition. But we don't need it on all of R. Clear? Now for your question, suppose you have a function whose derivatives are hard to calculate and the pattern is maybe more complicated. So arguing an argument like this would be harder. Yep. Okay? But still, if you want to use this theorem, in this sufficient condition theorem, then you're going to need to show this. You're going to need to argue this. Okay, so for sine it's easy, for cosine it's easy, for e to the x it's rather easy. For other functions, it could be harder. Yes?
And we could generalize the second example as well by saying on an interval like a minus b and a plus b. And then
What do you mean a minus b and a plus b?
Like here you chose symmetric interval.
Right. We're doing everything except the statement of the theorem. Everything we did, we just took a to be 0 in the calculations. So we did this example about 0, so here it's a symmetric neighborhood of 0. If you would take a function and do the expansion in a neighborhood of a, then you would need this to hold on a neighborhood of a. And in this example, it would be just as, the statement would be just as easy. Still be the right end of the neighborhood. That's where that would give us an upper bound. Okay? More questions? Okay, so the fact that most nice functions satisfy this condition is what makes the Taylor theorem so useful. Okay? So I can't give you a theorem that says, for example, all elementary functions satisfy this condition. It's not exactly accurate, because elementary functions can have problems with their derivatives, remember? All we can say about them is that they're continuous on their domain, but differentiability becomes an issue. But you can maybe phrase more precise statements, but the general concept is most good functions would satisfy this, and therefore enable Taylor expansions that are meaningful in the sense that going to higher degree polynomials gives you better and better approximations. Okay? So you will do many more examples of Taylor applications in homework and in discussion. And I think we're going to have a break now, and after the break, start the second part of our course, namely snakes. Okay, so let's have a break.